We're on to Unit 3 grid review. Unit 3 was over modeling and analyzing exponential functions. This was in November and December, so right before we started finals week. So with exponentials, there's a couple questions I want to go over. Remember, we've got our topics first column, ideas to recall second column, and practice problems for our third one. Make sure you're reading through the ideas to recall column just to give you some ideas about some important hints to kind of help you answer those practice problems. So the first one I wanted to go over is on the front page, and it's talking about determining if a function is exponential. So remember that exponential functions have multiplication or division patterns, or there will be a constant ratio present in the table. And that's what we're going to look at for constant ratio, is number 5 here. I wanted to look at this because I noticed last week when we were practicing our table work ratios that a lot of people were doing it incorrectly. So I just wanted to show that work quickly. So whenever we're finding a ratio, we're comparing the y values. So we're going to be doing our original y value of 1, and we're going to be dividing that by 1/3. Now, splitting 1 and we're dividing it into thirds, it's basically saying 1 divided by 1/3, which would be the same thing as 1 times 3 in this case, because it's basically asking how many thirds are in one whole. There's 3 1/3s in one whole. So we're dividing the y value we have by the previous y value. Here, 3 divided by 1, that ratio gives us 3. And here, 9, our y value divided by the previous one of 3 gives us 3 as well. So we've proven that this is an exponential function by finding the ratio. Since there is a common ratio, we know it's exponential. But again, keep in mind that finding constant ratios have to do with the y values, dividing the y value by the previous one. The next one I want to review is number 7. Similar to arithmetic sequences, geometric sequences are multiplication and division patterns with an explicit and recursive formula as well. Except for instead of a common difference, we're going to see a common ratio in this case. So again, we saw ratio here in number 5. We're looking at ratios again. So to find the first 5 terms in number 6, we just substitute a 1 in, a 2 and a 3, and that's not as difficult. But here, we're going to practice writing our explicit and our recursive formula. So what we need to find for both of these is our R value, which is our common ratio. And our common ratio in this case would be what we're multiplying by, which is 3 to get to 9 would be times 3. 9 times 3 gives us 27. If you did not know what we multiplied by to get the next number, you also could have done the y value, 9, divided by the previous value of 3. 9 divided by 3 also gives us 3. So that's another way to find ratio if you're ever not sure. Or if you're ever not sure how one value gets multiplied to the other, just divide the two and it will tell you. So our explicit formula in this case, we would have a sub n, because we're writing an explicit formula that we could use for any term number, equals a sub 1. And where I'm looking is right here on the side that we just outlined. A sub n equals a sub 1. A sub 1 is our first term, and our first term is 3, multiplied by r, which is our common ratio or our pattern, which would be 3 to the n minus 1 power. You can always test to see if you're correct. Let's take this. The second term is a 9. So 2 minus 1 is 1. 3 to the first is 3. 3 times 3 is 9. You can always check to see if you're right. Now, recursive formulas, we again start with a sub n. But this time we're going to put a sub n minus 1 in our equation because that represents the previous term, the term that came before. And we're multiplying it by our common ratio of r, which was 3. So if we wanted to find the second term, we would take the first term and multiply it by 3. If we wanted to find the 10th term, we would take the 9th term and multiply it by 3. The last one I want to do with y'all is on the second page. It's over modeling exponential functions in scenarios and evaluating. So remember that exponential functions are written in the form of y equals a times b to the x power. And just like yesterday with our linear equations, we're going to be reading a situation, defining our x and y values, and then determining what month 3 would look like in this case, or in this problem, hour 9, whatever it is. So write the equation and list the population for month 3. A chipmunk population doubles every month. Starting with 2 chipmunks, what is the equation that models the situation? So if we look here to our standard form, we would have y equals, A is our starting value, which is 2 chipmunks, so that represents our A value. It says that our population is doubling. Doubling is multiplying by 2 every month. So our x, what that represents, if we were to substitute numbers into our x value, our x represents the months. And when we do that mathematics, 2 to the power of whatever month times 2, what we're finding is the number of chipmunks there are. We're looking for that population. So here, if we were deciding what month 3 was, we would substitute a 3 into our equation for x. 2 to the third power is 2 times 2 times 2, which is 8. 8 times 2 is 16. So we know at month 3, there would be 16 chipmunks. Remember, a lot of people try and define x and y as numbers, but we're looking for a variable in that case. Remember, I have a PDF and a Word version attached in the assignment, so please feel free to fill out any one. The answers will come out at 2 o'clock today, so if you turn your paper in before 2 o'clock, I would like you to go back and check your answer key once it's turned in. If you turn your paper in after 2 o'clock, I would like to see some check marks and revisions and edits as needed on the assignment as you turn it in.